it wasn't enough evidence for me to reject the possibility that they are the same. Okay. So the rule is we pick something called, we pick alpha, which is known as the significance level. Okay. And in general, alpha is usually 0.05. Okay? And we say if our p-value, if the p-value that we get is greater than alpha, then we say that the difference we observed is not statistically significant. And we say, you know, our difference, y bar 1 minus y bar 2, is not statistically significant. And that means we are not, we will not reject the null hypothesis. There is a non-negligible probability of observing data like ours or something more extreme when the null hypothesis is true. So if the p-value is bigger than alpha or bigger than the significance level, we do not reject the null hypothesis. So so you're asking, when is the p-value not small enough? If the p-value is bigger than alpha, it is not small enough. Okay? It's too big for us to just disregard the possibility that the null hypothesis is true and that I observed my data from random chance alone. On the other hand, if the p-value is less than alpha, then our observed difference is statistically significant. Okay. And we choose to reject the null hypothesis. And what we are basically saying is that it might be possible for us to observe the data, to observe our data when the null hypothesis is true, but that possibility is so small, I'm going to choose to ignore that possibility, or choose to throw out that possibility and just conclude that my null hypothesis is wrong. Okay? So let's say we were looking at maybe another species. Okay? We said our some new species that we haven't seen before. Okay, it's brand new. we observe 10 males and we observe 10 females. And there's a sizable difference in the average weight in our sample. Okay, the sample of males have a large average weight. The sample of females have a smaller average weight. And we're saying, is it possible that in the population the males and females have the same average weight? I suppose it's possible. But the probability of me seeing 10 males where the average is here and 10 females and the average is down here, the possibility of that happening from random chance alone is so small that I'm going to just ignore that possibility and come to the conclusion that the populations do have different mean weights. Okay? So if the p-value is small, then we say our observed difference is statistically significant. We choose to reject the null hypothesis. We are choosing to say that the possibility or probability of observing our data or something more extreme. I'm just going to abbreviate that, SME. Or something more extreme is so small, or under the null hypothesis, is so small that we can ignore it. So small that we can ignore it. And so this is the mindset that we have when it comes to hypothesis testing. We're asking, if we assume the null hypothesis is true, what is the probability of observing our data? Okay? And so by default, we might choose alpha to be 5%. Okay? But this line is very arbitrary. Okay? It's just after years of research, or just after years of studies being published, 5% has somehow become the number to use. Okay? But it's very arbitrary. Okay? And there's a slight danger. Okay? Because you might get a p-value that's 6%, and you say, okay, well, my conclusion is not significant. And then you get a p-value that's 4%, and you say, oh, okay, now it's suddenly significant. Okay? There's a slight danger, and because of that, this method has come under a lot of criticism, because there's kind of like this, not a whole lot of critical thinking, and we just say 6% not significant, 4% significant. It has come under criticism for that reason, but that's, I don't know, this is hypothesis testing in its basic form, okay? And so I think originally the intention was that you as a researcher would have to come to a decision prior to doing the problem and say, at what point am I willing to reject the null hypothesis? Okay? And you'd pick a level. And maybe that would be 5%, maybe it was something higher, maybe it's something smaller, and it should depend on the circumstance of your research question. Okay? And then as the study, as you collect your data and you do the thing, then you would make your decision that way. Okay? It's just unfortunate that, you know, a lot of journals won't publish papers unless the significance level is under 5% and things like that. And so there's kind of this mentality of this is what happens, and let's try another problem here. Okay. Or actually, let me talk a little bit more about our choice of alpha. Okay. So the significance level alpha should be chosen by the researcher prior to analyzing the data. So your choice of alpha corresponds directly to what we call a type 1 error. Okay, so when you go through a hypothesis test, at the end of the hypothesis test, you're going to have to make a decision. You either have to reject the null hypothesis, or you say, I'm not ready to reject the null hypothesis. Okay. So at the end of the test, decision. Either reject the null hypothesis, and this happens when your data has a difference that's large enough for you to say, this difference probably didn't happen from random chance alone. Or you do not reject the null hypothesis. Generally happens when the data you have produces a difference that's not that large for you to say it's statistically significant. But these decisions, you're hoping you're making the right decision, but it's very possible that the conclusion you make is wrong. Okay? So ideally, when the null hypothesis is true, meaning when mu1 does equal mu2, we do not reject the null hypothesis. Okay? Ideally, we don't reject the null hypothesis if the null hypothesis is true. Ideally, when the null hypothesis is false, or when mu1 doesn't equal mu2, we reject the null hypothesis. But our data could lead us astray because of the random nature of our selection process. Okay. So when the null hypothesis is true, we would expect that whenever we take two random samples, they would have similar sample means. But it's possible that from random chance, the sample means we get have a significant difference. Okay? And we go through the test, and the test tells us that this difference is statistically significant. Okay? But the entire time, the populations actually have the same mean. And just from random chance, it's possible that we get two samples that are different enough for us to make the wrong conclusion. Okay? So for example, if we look at the entire population of the United States, the average IQ of men and the average IQ of women are roughly the same, okay? However, if we take a random sample of men and a random sample of women, okay, most of the time, those two samples will have similar average IQs. But every once in a while, we might get two samples where the average IQ is statistically significant, okay? And that could happen just from random chance alone. And in that case, we would go through the process, and by following the process, it would lead us to conclude that the means are actually different, okay? Yes?
And you could have a case where the population means are not equal, but the two random samples are equal?
Exactly. Okay, so let me focus on the first one first, and then we'll talk about the other situation, okay? So ideally, for average IQs of men and women in the United States, ideally all of our samples would reflect that idea, okay? It would not contradict that. But because of the nature of random sampling, it's very well possible that we just get kind of this unusual sample that leads us to the wrong conclusion. And that could happen in any situation, okay? I'm looking for a spot to write this. But because of random sampling, we might get some samples that lead us to the wrong conclusion. Okay, so, the truth is, mu1 is equal to mu2. So that means the truth is the null hypothesis is true. But our data leads us to conclude to reject the null hypothesis. Okay, so our data leads us to conclude that the means are different. This is a mistake. This is called a type 1 error. And use Roman numeral 1 there, okay? So type 1 error is rejecting the null hypothesis when the null hypothesis is true. And that could happen just because our random data was weird. How often would we commit a type 1 error?
5%.
Yeah, we commit a type 1 error whatever level of significance we choose, okay? So the probability of committing a type 1 error is equal to the significance level. Is equal to alpha. Because if we're saying alpha is 5%, we're saying whenever the probability is less than 5%, I'm going to choose to ignore the possibility that it happened by random chance and conclude that the null hypothesis is wrong. But the truth is it could have happened by random chance 5% of the time. And so the probability of committing this type of error, type 1 error, is the significance level alpha. So if our significance level is 5%, we will make this type of mistake 5% of the time. So our choice of alpha reflects our willingness to make this kind of mistake. So if we're willing to make a type 1 error, quite often, we can choose a large alpha. If we're unwilling to make this mistake very often, we would choose a small alpha. So our choice of alpha reflects our quote willingness. Make a type 1 error. So when the null hypothesis is true, our data could lead us to conclude that the null hypothesis is false, just because of the data was just unusual. All right. And then the flip side is equally possible, or not equally possible, but it is also possible. Okay. So ideally, when the null hypothesis is false, our data would lead us to that conclusion. Okay. So, silly example, men and women, on average, men and women have different average heights. The average height of males is taller than the average height of females. Okay? Whenever we take random samples of men and women, our random samples should reflect that. If we take a random sample of men, the average height of men should be taller than the average height of the women, okay, in our random samples. But because of random sampling, it's quite possible that I get a random sample of men and a random sample of women where that difference is quite small. Okay? The averages might not be exactly the same, but the difference in the average heights could be small. And because it's small, we might come to the conclusion that that difference is not statistically significant, and then we would come to the conclusion that the average heights of men and women, or we would not be ready to reject the notion that the average heights of men and women are the same. Okay? So let me write that down. Okay. Can I erase this? So we could also make another type of mistake. So the truth is, so in another scenario, okay, mu1 does not equal mu2. So the truth is, mu1 does not equal mu2, or the truth is, the null hypothesis is false. Right? So for example, mean height of men is not the same as the mean height of women. Okay. Ideally, our samples would reflect this. But because of random sampling, could produce two samples where the difference is not very large. Could lead us to the wrong conclusion not to reject the null hypothesis. Okay. This is called a type 2 error. Type 2 error is not rejecting the null when the null is false. We do not reject the null. The probability of type 2 error is known as beta. Okay. The calculations behind beta are kind of complicated. They're kind of a pain in the butt. So we're not going to go into how to calculate beta. You don't directly have a choice of beta as you do alpha. So alpha, as the researcher, you get to choose. You don't really get to choose beta. Beta depends on other factors, primarily what the true difference in the populations are. Okay, but in general, if you choose to decrease alpha, so you're trying to lower the probability of a type 1 error, by choosing to lower alpha, you generally increase beta, okay? Because lowering alpha means you are rejecting less often, which means the possibility that you didn't reject when you should have goes up, okay? So in general, choosing a small alpha means beta is large. And on the other hand, choosing a large alpha will give us a smaller beta. Okay. So there's this constant balance between type 1 error and type 2 error. Maybe we are less willing to make type 1 error and more willing to make type 2 error. Or maybe we are more willing to make a type 1 error and less willing to make a type 2 error. That will reflect whether we choose a large alpha or a small alpha. Okay? So let me just give us a couple examples without math that might reflect whether we should choose a large alpha or a small alpha. So just remember, keep in mind that the data is always used towards rejecting the null hypothesis. It's never used to try to prove the null hypothesis true. It's either the data gives us reason to reject the null hypothesis, or the data does not give us reason to reject the null hypothesis. Okay. It's always used. Towards rejecting the null hypothesis. Okay, so think of a smoke alarm. Alright, with a smoke alarm, what is the job of a smoke alarm?
Tell you whether there's smoke.
Okay, so it has two jobs. Number one, when there's a fire or when there's smoke, it's supposed to sound an alarm. What's the other job? And it's so obvious that you don't think about it until it doesn't do this job.
Keeps you alive.
To be quiet when there's no fire. Okay, those are the two jobs of the smoke alarm. And you don't think of the second job until it's malfunctioning and not doing it. Okay, so Number 1, sound an alarm when there's a fire. Number 2, be quiet when there's no fire. All right, what do you think? And what it does is, if it detects smoke, it sounds the alarm. Okay, so in our case, the null hypothesis would be what? There is a fire, there is no fire. So the null hypothesis is that there is no fire. The alternative is that there is a fire. Okay. The data he uses is smoke. Smoke in the air. And the smoke is always used towards rejecting the null. Okay? And so, if it proper function is rejecting the null when there's a fire. Reject the null, sound an alarm. When there is a fire, meaning null is false. And also proper function would be not rejecting null, not reject null, silence, when there is no fire. Null is true. What is a type 1 error in the context of a smoke alarm? Alarm goes off when there's no fire. Type 1 error is alarm goes off, or alarm sounds, I should say. Alarm sounds when there's no fire. So this is rejecting the null when the null is true. So that's type 1 error. Type 2 error, on the other hand, would be what? Type 2 error would be silence when there is a fire. Okay, silence would be not reject when the null is false. Is that all right? So between these two mistakes, two errors, which error is worse? Type 2 error is worse, right? Type 1 error is annoying, but type 2 error could be tragic. So type 2 error is worse. So in this context, should we pick a large alpha or a small alpha? So alpha reflects our willingness to make a type 1 error.
Large alpha.
Okay? So we are more willing to make a type 1 error than a type 2 error. So we would pick a large alpha. Okay? Is that okay? So that's a situation where you want a large alpha. Okay. All right, let's talk about the other situation, okay? can you think of another situation where you want a small alpha? And actually, maybe not smoke alarms, but carbon monoxide detectors. Actually, today they're, I don't know, maybe more calibrated correctly, but in the beginning, carbon monoxide detectors used to be extremely sensitive, and some instruction manuals would say the first time it goes off, it's so sensitive that the first time it goes off, it could just be a false alarm. So reset it, wait an hour, and if it goes off again, then clear out the house. But maybe that's bad advice. So I think they stopped saying that. But they used to make them really sensitive, okay, and because it was that type 1 error was more likely than anything else. Okay, another situation, but just the opposite. Think of a criminal trial. Okay. They say the burden of proof falls on which side?
The state.
On the state. Okay, so the prosecution. So when they're prosecuting the defendant, okay, the null hypothesis would be that the defendant is innocent, and the alternative is that the defendant is guilty, okay? And the data or the evidence is used towards rejecting the null. Okay, so it's the prosecution's job to present enough evidence to convince the jury that the null hypothesis is false. Okay? If the prosecution doesn't have enough evidence, then the trial gets dismissed or whatever. Okay? So if there's not enough evidence, you conclude not guilty. Doesn't prove innocence, it just means not guilty. So the proper decision is when the null hypothesis is true, the defendant is innocent, the defendant is acquitted. How do you spell acquit?
A-C-T-U-I-T.
Q-U-I-T. Acquitted. Okay. And the proper conclusion is that when the null hypothesis is false, defendant is found guilty. Then we have what we would call failures of our justice system, okay? So in the United States, failures of our justice system could be considered type 1 errors or type 2 errors. What would be a type 1 error? Rejecting the null when the null is true. Yeah, so finding an innocent person guilty. So the jury concludes guilty when the defendant is innocent, okay? Type 1 error would be finding an innocent person guilty. So that's rejecting the null. And the null is true. Type 2 error would then be what? Acquitting a guilty person. So someone is actually guilty, but the jury acquits the person. Okay, so And so, there might be some disagreement here, but in terms of, in the formation of our justice system, when I guess the framers or the founders of our country created our justice system, what did they say was the worst error?
Including a guilt.
They said a type 1 error is worse than a type 2 error. They said, we'd rather let guilty people go free than put an innocent person in jail. So, so the type 1 error, is worse. So would we choose a large alpha or a small alpha?
Small.
Small alpha. We don't want to be rejecting the null hypothesis on a whim. We want to be absolutely sure. So we choose a small alpha. Okay. And they actually tell the jury this. They don't say choose a small alpha, but what do they say?
Beyond a reasonable doubt.
They say beyond a reasonable doubt. Okay, make sure you are certain beyond a reasonable doubt. They don't want people to just say, seems guilty, so we're going to say guilty. Okay, they want to. If you're going to say guilty, you want to be certain without beyond a reasonable doubt. Okay. And so, sometimes in high-profile cases, everybody watching on TV is like, oh, this person for sure is guilty, and then the jury concludes not guilty or something, and then people get angry or whatever. But that is inherent in a system where we choose a small alpha, where any time you can kind of poke holes into the prosecution, we encourage type 1 error over the type 2 error. Okay, let's take a short break, and